This video is about where linearity shows up in different scenarios. So linearity is the general concept that when you take a linear combination of the inputs, the output must be the corresponding linear combination. You have some process that takes, say, C times input 1 plus D times input 2. And after doing the process, you have to get, so if you think of this as your input, then the output of this has to be C times output 1 plus D times output 2. And when you have a process like this, that's called linear. This process is linear. Some process, something that's taking inputs and producing outputs. I mean, this process is the same as a function, right? It's some function or some operator. That's another term that's used. And it's something that takes inputs and outputs in a particular way. If it does this, then it's a linear process or linear operation or mapping. So some instances where this shows up is in matrix multiplication. We've seen that if I have a matrix A and I take a linear combination CV plus DV, CV plus DW, and I take A and multiply it by that, I get C times AV plus D times AW. So just to make sure we're okay on the notation, C and D are scalars and V and W are vectors. I get this vector. I take my matrix A and I multiply it by this vector. I get C times AV. Well, A is a matrix, V is a vector, so AV is a vector. Similarly, AW is a vector, and so this is a linear combination of these vectors. Right? So matrix multiplication is linear. A second place where it shows up is in differentiation. So if I take the derivative of a constant times a function, say f of x, plus another constant times another function, d times g of x, this is the same as c times f prime of x plus d times g prime of x. So here my process is the derivative, and my inputs are actually functions, and I'm applying the function and getting the derivative. So I take f and I get f prime, I take g and I get g prime, and then the general theory of derivatives says that if I take a linear combination of f and g, I get the corresponding linear combination of f prime and g prime after applying the derivative. So we say that differentiation is a linear operator. Now notice that this is a very different scenario than matrix multiplication, right? I mean, it's a completely different scenario, but you still see this linearity property. And then the third scenario where you see this is in differential equations. So if I have something like y prime plus 4y, okay, if I take y to be a linear combination of two functions cf plus dg, if I take that derivative plus 4 times cf plus dg, this is going to be c, let's see, it's going to be C f prime plus 4f plus D g prime plus 4g. You see, this is my input upon applying y equals f. That's my output applying g as my y. And then when I make my cf plus dg my y, I get the corresponding linear combination of the outputs. Right? So this is related to example 2. And I get this linearity property. And because these three are different scenarios, but they all have linearity, the consequences you get from the linearity apply to all three different scenarios. So, for instance, whenever you have a linear operator, the solutions to Tx equals b, so has solution xp, so that's a particular solution, plus xh, which is the homogeneous solution. So the homogeneous solution is the solution to t of x equals 0. So in the case of matrix multiplication, that's reflected in the fact that the general solution of ax equals b is going to be xp plus xh. Okay, so these are the solutions to ax equals 0. Those are the vectors in the null space of A. And this is something we've seen before, that when you have a system of linear equations, the general solution is either going to have one or infinitely many solutions if your system is consistent. If your system is consistent, then it's going to have at least one solution, say xp. And if it has any other solutions, those solutions are going to be obtained by adding a solution to ax equals 0 to that particular solution. So the system ax equals b has infinitely many solutions as long as there are non-zero vectors in the null space of A. And how is this reflected in the stuff about derivatives? So the general solution, if I have a function, say f, then my general solution to the derivative of capital F is little f is, oh, do I want to use capital F? Maybe I'll use g. So I'm looking for all the functions whose derivative is little f. It's going to be a particular antiderivative plus a constant, right? This capital F of x is one antiderivative. It's one function, it's a particular antiderivative. Maybe I'll just write it like this. Particular antiderivative, and then these constant functions, why do I need to add constant functions? Because these are the functions, remember I'm adding a constant function, not like a constant number, I'm adding a constant function. These constant functions are functions that are in some sense, the null space of this differential operator ddx. Now ddx is not a matrix. I'm saying that the null space, or sometimes called the kernel, refers to all the elements that the operator maps to 0. And there's a theorem that if you have a function whose derivative is 0, that function must be a constant. And that explains why you add these constants to your capital F of x, right? So for instance, if you have something like the derivative, oh, see, I don't want to use little f here, because if the derivative of g is, say, x squared, then that tells me that my g of x is going to be 1/3 x cubed plus a constant, right? This 1/3 x cubed is one function whose derivative is x squared, and then all the other functions are obtained by adding a constant c. So this C is like the null space of my matrix A. Okay. And then in differential equations, again, it's this xp plus xh. So the general solution, if I have a differential equation like ay double prime plus by prime plus cy equals some function like e to the x or something, the general solution has the form y equals yp plus yh. And my yp is one solution to this differential equation, this non-homogeneous differential equation, which I'll call star. And then yh is the homogeneous solution. It's the solution to ay double prime plus by prime plus cy equals 0. So now the way I'm thinking about this differential equation is I'm thinking of this whole thing as my, on the left is my operator. And this homogeneous solution is the null space of that operator. Okay, it's the null space of the operator that maps a function y to ay double prime plus by prime plus cy. And that's why when you're finding the general solution to this non-homogeneous differential equation, there's two steps. First, you have to solve the homogeneous equation. That gives you the yh. And then you have to find the particular solution. And for that, you use these different methods, like the method of undetermined coefficients, variation of parameters. And so that is a consequence of the linearity. Okay. So the concept of linearity goes way beyond matrices. Okay, this matrix multiplication is one instance of where you see linearity, but linearity is like a general principle. It's like the general thing that you see in lots of different, should I say lots of different places? In at least 3 different places, right? The first one is linear algebra, the second one is calculus, and then the third one is differential equations, which you can also think of as, I guess, as calculus. And then a fourth one is, I'll just say it really quick, if you have a definite integral, so an integration, let's say you are integrating a function from 1 to 2, right? If you're integrating the function cf plus dg from 1 to 2, that's the same as, see, there's this property of the definite integral that's c times the integral from 1 to 2 plus d times the integral from 1 to 2 of f and g respectively. This is a linearity property of definite integrals. So I guess you can also think of this as a linear transformation of some sense. It's taking a function to the definite integral. So it's a linear transformation from one space to the real numbers. It's a space, the input space, the domain is in Rn or Rm. It's a space of functions. So that's why when we're looking at general theory of linear algebra, we need something called vector spaces. You're talking about linear transformations from one vector space to another, and it's not necessarily from Rn to Rm. Okay, that's all I wanted to say about this video. It's not really about linear algebra, but it gives you some more perspective on how linearity shows up in different areas of math.